So the last two clients I had made the same mistakes about their AI SaaS system. And it all relates down to just basic queuing architecture. And it's one of the things that I've given a talk on. You can go check that out up here, wherever you want. But here's the thing that they did not get. But before we get into that, my name is Zach Clifton. I've been an enterprise architect for most of my career, working on large-scale systems like solar integrations or notification systems. If you're someone trying to scale your software either with or without AI, check out my link below in the doobly-doo for a free consultation. So they would have tasks like this. So I would have, let's say, some LLM here, and this would produce some set of events. So when it created an event like this, they would go and put that into a queue. I'm just going to use the long. So we're just going to name this Q1, right? So then another LLM function would go pick it up. So this is great until they start to chain these together. So when they started chaining these together like this, so it essentially looks like this, right? So they have some LLM that generates an event that goes into a queue, that goes for an LLM, and essentially either goes back or goes back into the queue itself. So in this way, their biggest problem here is that they can't scale this very well. So they can throw up more systems here. But the issue is, so this is the example here. Basically, they would have the first LLM function creating a bunch of events to go basically out to LinkedIn. And then as they go and process each one of these events, it'll come back with either people or companies that they need to go again, reach out, get that data and have the LLM process. But the problem is over all of their clients, even though this may look good at the beginning and it's super simple to make and validate, the problem you quickly get into is that as soon as I start adding more tenants, we're just going to extend this on here, right? So this just becomes a big long line and it causes the head of the line problem. And the head of the line problem essentially states the following: the worker system cannot evenly distribute workload over multiple tenants because whatever's in the front has to be processed first. Most people will go and say, oh, well, crap, this is taking too long. We need to go split these queues up. And so this is an example of a single queue, okay? This is the first version of queuing, single queues. And from here, people will go and do what's called multi-queue. So this is where you get this situation. So I'm going to have LLM1 generate an event to go into Q1, and then LLM2 generate, once it gets this data, go and generate more data here. The problem is this though. So even though I have multiple queues, this doesn't account for multi-tenant. The simple way to solve this is I'm going to have a high priority queue, a medium priority queue, and such on. But the problem with this is you still run into the same problem. And this doesn't even account for all the infrastructure you have to have in terms of the LLMs and worker functions and deployments to even make this work well. And so this is where we were with these clients, and it just becomes a giant headache to try to scale this. And you can't. And at the base of it, you cannot scale this kind of architecture with queues. So what you have to do is, and I'm going to call this is the false multi-queue, because you think you're doing all this bucketing and fancy stuff, but you're really not solving the problem. To solve this, you have to answer the following question: what is my atomic piece? Okay, and what is a piece? Well, this is basically the smallest unit in your data. So most companies will have a tenant, then they'll have some workflow, and then inside that workflow, they'll have let's say a step, some action, right? And that action is a parallelizable unit of work, right? So I can have a bunch of these things happen at the same time. Customer 1 puts 1 million events into this queue. I'm going to have to go through 1 million events before I can even get to customer 2. So now, basically, a true multi-queue system says that per each one of these sets, I'm going to have a queue. So for this step, I'm going to have my tenant T with my workflow W and my step, let's just say step 1. The same thing, but for a different tenant. So this will be unique. So we'll have like, let's say T2 for workflow and then step 1. And so we can have these differentiated by tenant, but typically tenant is not enough, right? So, and it also depends on your architecture. If I'm going for something like BullMQ that's TypeScript based, that at the pro level supports virtual multi-queuing. But if you're going something for more high scale like Kafka doesn't support something like this. So you have to take a different approach. I have to then bucket. This is option 1, right? Basically virtual queues. So then that brings us to option 2. So option 2 here is basically what we call bucketing. Now this will work for Kafka or Pulsar-like systems. My preference is always Pulsar over Kafka just because of the actual scalability that it has over Kafka. With bucketing, essentially, I'm doing the same thing as I'm doing with virtual queues, but I'm doing it at an infrastructure level. So I have to, in my application code, I can't just have to go to this queue and it automatically happens with like a virtual queue. So again, BullMQ, Celery, Nats kind of does this itself with subjects. And Nats is my choice system always for any greenfield system nowadays, just because it combines so many things into one. It makes it super easy to use. But with bucketing, essentially when I do this, when I have my events go in here, I'll have my events go into either this one, or I specify and go it into this one. So we're bucketing. But the issue with bucketing is that I have to set these up beforehand. And this is not an application change. This is an infrastructure change. And if you're running with separation of concerns, this becomes a much bigger problem. We've essentially traded one set of problems for another set of problems. So, and we know exactly what not to do with a false multi-queue. This one will always cause issues. This is the thing most developers reach for, bites them in the butt real fast. So how do we fix this? Like, what do we need to do to make all this go away? Well, first I want to say this, unless you're sending billions of events per second, and very few companies are at that level, this works perfectly fine. This will get you very far, but at some point it won't. It's not enough. And when you get to that point, like I did when we were working at Novu, we had to start working towards doing the actual solution to this, which is called dynamic queuing. Now, the key difference with this is that dynamic queuing has a mediator, otherwise known as a coordinator, or like what my clients like to call it is air traffic control. And it actually kind of works since I'm a private pilot too. So essentially, we're going to have a fleet of workers. Okay. So these workers need to figure out what queue they need to work on. Now, this is different from every model we've talked about so far, because every other model that we have here, whether that be the true multi-queue, false multi-queue, or the single queue system, all of these workers, these LLMs, have hard-coded, this is the queue you go to, and this is the queue I pull from. That's not how it works with the dynamic queue. So whenever you have a fleet of workers, each worker is going to first make a call to air traffic control. So the worker is going to ATC, they're going to make the call all about who am I, and the ATC is going to look at their system and basically do a lookup. Now, this is why I like Nats as a solution for this, because Nats not only has the queues built into their system, but they also have key value. But this could be easily Redis, Dragonfly, or whatever else. It just needs to be a key value backend. And so ATC knows what it needs to look at. So then essentially what we're going to do from here is that ATC is going to query its key value store and say, okay, this worker is part of fleet ID 0, 01, and it's going to get whatever conditions it needs. So that's going to be that it can only work on tenant ones, right? So we have it high enough scale where this fleet of workers is specifically just for tenant one. Now you can just do this as a premium offer or whatever else, but once we do that, then we need to make the next query. So from here, once we have the fleet ID, we're then going to need to make a queue to the queues. Now, why do we need to make a call to like getting the data of the queues? So it's really important with dynamic queuing that you understand what each queue is doing, because we don't have set allocations for each workers. Each of these workers, we're looking to say which of these queues are the ones that need the most attention, because you can see here, this one right here has a side of 10,000 and it's adding 2K events per second. Let's just say for the simplicity, okay, this is the largest queue going on. Now, in reality, this would be a background process having this all done in a time series database like Timescale DB or ClickHouse. All of that stuff would be aggregated and materialized so you can see which ones are the bigger ones, and so you can allocate your systems as needed. But once we have that data, we can now send back to the worker that you need to work on this queue. So this is number 4, the response. And when we get this response back, our worker in this fleet will now know this is the queue I need to start operating on. And now that I can start operating on it, it will work until it's gone. There are essentially a few different flavors of this. So either one, my queues can persist after this. So let's say I'm doing stateful systems where I know that I'm having consistent flow of this, let's say I'm doing some stateful system that has a consistent flow, like for example, log replication on a database, and I'm trying to replicate that from region to region. So from here, this queue would stay up, and this would be something that we would have here in our queue data. So since it's true, we know this queue is never going to go down, but we may need to change allocations. That's where workers will go and heartbeat ATC and call, hey, I'm at 6 Mile Island. What do I need to do? Then the ATC will be like, hey, stand by in a holding pattern outside, right? So it may be that I need to wait, and that's okay. But we have this done. But essentially what ATC here is, it's the brain behind it all. This is the piece of dynamic queuing. Now, there's a lot of extra pieces to this. Like, for example, ATC will also typically call out to your infrastructure system that is running your queues up here. So if it's calling out to AWS, let's just say you're on AWS Fargate, just to keep this simple and not go in the Kubernetes world. But let's say you're running on Fargate. So now I'm having to build in a bunch of AWS specific APIs to my ATC to be able to say, hey, I need another fleet of these. I need to do this. And typically, in my experience, the best way to implement stuff like this is to actually leverage a Kubernetes deployment system that allows you to essentially say, hey, I just need another one of these deployments with this kind of stuff. And that could also be, you have a centralized config where you have a nice no-code dashboard to kind of put those stuff in there for your salespeople and things like that. But that's how I've seen it best implemented. But at the core of this, the thing is this. You start out with single queues, and this is okay for validation, and that's about it. You get into the multi-queue, but you have to be really careful about implementing it, because if you just do high, medium, and low, then all you're going to do is have the same problem as a single queue, just with a lot more headache. And so you have to go to a true multi-queue system where you're either doing virtual queues or bucketing. In either case, the infrastructure requirements increase. But at the very high scale of things, you'll have dynamic queuing. And so dynamic queuing is the most scalable and most efficient piece out there. Because what I didn't also say earlier was, let's say this one's permanent, but this one's not. So this one would have been an example of like my old company, Novu, where we would have workflows that would be done in and out of the day. So one company's workflow may happen at 2 a.m., but another set of company workflows would happen at 5 p.m. And so these queues have to be able to come in and out of existence based on the workflow. Again, all controlled by ATC and typically your application. And so it requires a bit of analytics, and a lot of this stuff wouldn't be possible without having open source standards like the Grafana stack, where you can go and take live measurements of both of these systems and be able to make decisions off them. And in any case, this is how queuing happens at scale. And I think a lot of people don't recognize that this actually is just CPU scheduling at a infrastructure level.